In today's video, we are going to learn about laws of thermodynamics and their significance. Let us first understand the term thermodynamics. The word thermodynamics comes from the Greek words thermo and dynamis. Thermo means heat and dynamis means power. Thermodynamics is a significant branch of physics as it deals with the study of movement of energy and how energy creates a movement. There are 4 laws of thermodynamics: zeroth law, first law, second law and third law. Let us see one by one. First comes the zeroth law of thermodynamics. Zeroth law of thermodynamics states that if there are two bodies A and B in thermal equilibrium with each other, and the body B is also in thermal equilibrium with C, then eventually A will also in thermal equilibrium with the third body C. When there are number of systems in equilibrium, we know that there is a common parameter among them. By the term thermal equilibrium, we mean that the common parameter is temperature. That is, the zeroth law signifies temperature as a fundamental and measurable property of matter. What we perceive as the temperature of any matter or any system, it is the internal kinetic energy of the atoms or molecules. That is, the kinetic energy of internal atoms or molecules arises due to the vibrational, rotational or random motion of molecules. That is, kinetic energy is directly proportional to the temperature. As the kinetic energy of any system is high, the temperature of the system is also high. Then comes the first law. First law speaks about the conservation of energy. That is, the energy of any system can be converted from one form to another only with the help of interaction of heat, work and internal energy. That energy can neither be created nor be destroyed. Mathematically, the first law of thermodynamics can be given as del U equals Q minus W, where del U is the change in internal energy of the system and Q is the heat supplied to the system and W is the work done that can be retrieved from the system. So, the first law signifies about the conservation of energy. It also implies that in order to produce a usual work, we have to supply an equal amount of energy. First law also implies that the energy of the universe always remains constant. Internal energy of a system is a not accessible quantity and we can use first law to calculate the internal energy of the system. Then comes the second law. We see that the first law speaks about the conservation of energy, its amount and quantity, whereas the second law of thermodynamics speaks about the direction of the process, that is how the process will proceed or in which direction the process will proceed, and it also speaks about the quality of the energy. For any process to occur, the first law and second law of thermodynamics must be obeyed. Consider second law of thermodynamics. It speaks about the quality. By quality we mean that in any process there must be a heat supplied and that heat supplied must be equal to the work and some waste energy. As we saw in the first law of thermodynamics, that work cannot be 100%. That is, the high quality energy is not up to 100%. There will also be a minimum quantity of low quality of energy. This can be understandable with the following example. Consider a chemical bond. We know that chemical bond is much stronger, and when a chemical bond is broken, we get some high quality energy which is capable of doing work and some low quality energy that is liberated as heat. Here in this process, no energy was lost or created in the transfer, but the usability of the energy is declined in the transformation. That is, this low quality energy cannot be effectively harnessed to do any more work, so we cannot use one energy source forever. The second law of thermodynamics also speaks about the direction of the process. So, what is the direction of process? In any natural process in an isolated system, the process will progress in the direction of increasing disorder or increasing entropy of the system. The second law of thermodynamics also speaks about that heat energy will flow from hot body to the cold body until they reach thermal equilibrium. That is, moving a heat from a cold body to a hot body requires work to be done. Without any work, we cannot transfer heat from a cold body to a hot body. Then comes the third law of thermodynamics. In the beginning itself, we see that the kinetic energy and temperature are directly proportional. That is, as the kinetic energy goes on decreasing, the temperature goes on decreasing, whereas the kinetic energy comes from the movement of molecules. So this is the third law. The entropy of a system approaches a constant value as the temperature approaches absolute zero. From the figure we see that as the kinetic energy goes on decreases, the temperature goes on decreases and reaches a point that is absolute zero. So that is the maximum ordered state. that is the entropy reaches a constant value or near zero value. At this near zero, at this near absolute zero value, there is a fifth state of matter known as the Bose-Einstein condensate, and at this temperature, at this nearly absolute zero temperature, superfluidity and superconductivity occurs. Thank you.